Welcome back. I don't know if you noticed last time, I have a special tie on. It is my relativity tie. Huh? Okay, last time we learned about the twin paradox. You watched a little animated clip about it. And it was a little mysterious at the end. It just said there wasn't a paradox because the guy said so. It invoked the idea that one twin was accelerated and the other one wasn't, and that's certainly true. The one who took off for the distant star and then came back was accelerated all over the place, starting and stopping, while the other one who stayed home didn't have those experiences, but who cares? Why does that matter? Well, it matters because it breaks the paradoxical symmetry. The paradox is that one of them went at high speed and saw the other one's clock run slow, whereas the first one, from the frame of the second one, the first one went off really fast, and so his clock should be running slow, and so when they got back, each one is older than the other one, and that makes no sense. But if one of them experiences something completely different, well, then maybe their experiences aren't symmetric, and so there is no paradox. But that only works if the experiences they had make their clocks run different, and that's exactly what happens. Clocks also run slow when pulled on by gravity, and acceleration, as near as we can tell, is exactly the same as gravity. The force of gravity that holds you in your chair seems to be exactly the same as that funny force you feel when your car takes off from a stop sign. We have not been able to perform any experiment that can tell the difference between those two effects. Einstein said, well, if you can't tell the difference between gravity and being in an accelerated reference frame, then they must be the same. The mathematics to make that all work out is incredibly complicated, and we're not going to do that, and I'm not qualified to do it for you anyway. But that means that the twin who goes off to the distant star and has those accelerations also has his clock affected by the gravity that he feels, the fake gravity that he feels. Except now we don't call it fake gravity, we call it real gravity, since we can't tell the difference. That real gravity he feels, because he accelerates, makes his clock run different than the one who stayed home, and so they're not the same. And the one who goes off to the distant star and comes back younger, and that's just the way it is. And we have tested these ideas with sensitive atomic clocks in fast airplanes, and the GPS that you all like to use, which is so accurate and tells you where you are. That GPS doesn't work unless you put in the equations of relativity in the software that makes the GPS work. You'd be off by kilometers if it weren't for the equations of relativity programmed in the software of the GPS that you use. So yeah, the twin paradox seems to be real. All right, let's do some quizzes. Here's some questions from last time. If two events are simultaneous in one frame, they are simultaneous in all frames, moving with respect to the first. True or false? Give you a minute to think about that. And the answer is, it's false. Events that are simultaneous in one frame are non-simultaneous when viewed from a reference frame that's moving with respect to the one where they're simultaneous. How about this one? We did velocity addition last time. If a spaceship is traveling at 0.8 c, that's 8/10 of the speed of light, and shoots out a proton torpedo at 0.8 c in the same direction that it's traveling, a stationary observer from outside would see the torpedo go by at what speed? Newton would say 1.6 c, the velocity is just add, but that's not true. That doesn't work. And if you use the actual formula, it turns out to be c, 0.98 c. We'll practice this again a little later. Another question. It's okay for the space traveling twin to be younger than the one who stayed home when they get back together because Okay, which one of these is the best way of saying why the one who went to the distant star comes back younger? I'll give you a chance to read them. We just discussed this, so I imagine you all probably got it right. It's B. The traveling twin decelerated and accelerated, and that changes everything. Because he had those experiences, and the one who had stayed home didn't, and that makes their clocks be different. How about this one? We did the pole and the barn. The resolution of the pole-barn paradox is that, which one of these is it? Give you a second to think about that. It's B. The simultaneous events. That's where the barn is normal sized, the pole comes by fast, and its length contracted, and so it fits in the barn, and you can tell it fits because simultaneously the left end of the pole is at the left end of the barn and the right end of the pole is at the right end of the barn. In the other frame, where the pole is long and the barn is short, those two events still happen, but they happen at different times. First, the right end of the barn and the right end of the pole are together, and then later in time, the left end of the barn and the left end of the pole are together, and that's okay. You can have a long pole and a short barn and make that work. All right, now we're going to do the rest of relativity the way we're doing it here in Physics 123. So there's just a little bit of this and that in here. Here's the first one. If space and time are all mixed up when you switch frames, it means that the Doppler shift formula changes too, because that has to do with frequency and wavelength, and that's a time and space thing. So you'd expect the Doppler shift formula to change, and in fact, the frequency formula is different. This is not what we used for sound. If a source is approaching you, which makes the frequency upshift, that doesn't change. Approaching sources have upshift frequencies and receding sources have downshift frequencies. And if you run toward the source, the frequency upshifts, and if you run away from the source, the frequency downshifts. That all works the same way in direction, but the formula for it is different. It's the square root of 1 plus v over c over 1 minus v over c, where v is the relative velocity. You use this form with a plus in the top and a minus in the bottom. Both of those, both the plus and the minus, make the frequency shift up. If it's going away from you, you just flip the signs. You put a minus in the top and a plus in the bottom, and that's the frequency shift for something that's moving away from you. And you can read all about this in the book. So here's an example. We'll do this as a quiz. You should get your calculator out. I've given you the formula. A distant galaxy is moving away from you at half the speed of light. Light from that galaxy, which has a wavelength of 400 nanometers, which is deep blue, arrives at your eye with a wavelength of what? So I'll give you a minute to get your calculators out and think about this one. In fact, while you're doing it, I'll do it. Okay, well, if you do that carefully, you get the answer of 700 nanometers. And that's because V is still equal to lambda f. So if the frequency shifts down, the wavelength must shift up. That V and the V equals lambda f, that should be a C. When I post these slides, it'll be C equals lambda f. So in the formula above, you'd use V equals minus 0.5 C. And so f is downshifted by a factor of 0.5774, making lambda get bigger by 1.732, and 1.732 times 400 nanometers is very close to 700 nanometers. This means that with a big galaxy moving away from us at half the speed of light, means that deep blue light looks red to us. And you'll hear scientists sometimes talk about the red shift. This is how it works. Light from distant galaxies that are moving rapidly away from us are red shifted. Blue light ends up being red. Okay, let's review this frame velocity addition again. How does the frame velocity add to the motion of an object? So imagine that you're on a bus. The bus is moving at speed VAB. A is the stationary frame, and B is the bus moving. So maybe the bus is going 20 miles an hour down the street. And then from the back of the bus, you throw the ball at maybe 30 miles an hour. Galileo and Newton said that in that case, if you're looking at the ball from the stationary frame, those velocities just add, giving you 50 miles an hour for the speed of the ball. That's the good old 121 answer. That's obvious, but it's wrong. The correct formula is that you take the obvious thing, VAB plus VBC, the 50 miles an hour, that goes in the top. But in the bottom, you have 1 plus the product of those two velocities divided by c squared. For very small velocities, VA squared, VAB, VBC over c squared is really tiny, and so the Newton-Galileo thing works just fine. But if for speeds approaching the speed of light, that denominator matters. And you use plus signs if the velocities add together, and you can tell that just by looking at the situation. And you use minus signs if one velocity subtracts from the other one. You shouldn't just flail away at this, adding and subtracting velocities at random. Think very carefully about who's moving. Think very carefully about where the stationary frame is, then what the first moving frame is, and then what the thing that's moving relative to the moving frame is. And once you figure out what all those are and whether they're adding or subtracting, then you use the formula and you'll get the velocity as seen from the stationary frame A. So here's an example. While moving in a spaceship at speed half the speed of light, someone throws something out the back of the ship at 1/4 the speed of light. From stationary space, you see the object moving at speed. Which one of these? Give you a minute to think about this. The obvious answer, of course, is A. You're going to the right at half the speed of light. It gets thrown to the left at 1/4 the speed of light. You should subtract the two, and 1/2 minus 1/4 is 1/4. That's wrong. The answer is 0.29, and it's 0.29 because of that denominator down there. You take half the speed of light minus 1/4 the speed of light in the numerator, but then you have to also take 1 minus the product of those two, 1/2 times 1/4 down in the bottom, and that increases the velocity above the 0.25 that you get just from the numerator, and it makes it 0.29. Okay, so big deal. Galileo and Newton got the relationships between moving frames wrong. That doesn't seem so terrible. What's the big deal? Well, it wouldn't be a big deal if F equals ma and momentum and energy and all that stuff we did in 121. It would be okay if all that stuff were still the same. But what happens is it all has to be changed because the speed of light is the same in all reference frames. All of the physics that you studied in 121 is different. Okay, I got to make sure you can see this. This is my Albert Einstein t-shirt. And now we're going to talk about the good stuff. Okay, F equals ma just isn't true anymore. The other form of dynamics that we used, where the force is equal to dp dt, the rate of change of momentum, okay, that still works. But F equals ma is gone. You just can't use F equals ma in relativity anymore. F equals dp dt looks like the Newtonian thing, but it isn't, because that p thing isn't mass times velocity anymore. The momentum is gamma times mass times velocity. Written this way, mu, u is the object speed, so its momentum is mu divided by the square root of 1 minus u squared over c squared. And that's different. It means that objects have a speed limit. Look what happens if u starts to approach the speed of light. The denominator starts to go to 0. It means the momentum becomes enormous as the particle's velocity approaches the speed of light. And since the momentum is so big, it takes a lot of force or a lot of time, one of the two, to get it to go any faster. And what happens is that it just never can make it to the speed of light. It would take an infinite amount of energy being pumped into this particle to get it to go at the speed of light. So there's a speed limit on the way how fast particles can move. This momentum formula also means that fast objects have more momentum or inertia per unit velocity than slow ones. Newton doesn't say any such thing. Newtonian momentum is mu, and if you divide by u, you just get the mass, and it's a constant. But in relativity, you get gamma times m, and fast particles have more momentum per velocity than slow ones. And it doesn't agree with Newton, but it agrees with modern experiments. Everything isn't gone. This relativistic momentum, this funny gamma mu thing, it is conserved in the absence of forces. So we have momentum conservation for isolated systems. That doesn't change. That means that Newton's third law is still true. And so we have these two cornerstone laws, Newton's third law and momentum conservation. They still work. It's just the momentum is kind of funny. Okay, so here's what happens due to the fact that momentum has this funny structure and becomes enormous when you approach the speed of light. If you apply a constant force to a mass in Newtonian physics, since F equals ma, constant force means constant acceleration. Constant acceleration just means the velocity gets bigger and bigger and bigger at a linear rate, and the blue line is what you get for velocity versus time. It goes right through the speed of light and just keeps going forever, and there's no limit to how fast a particle can move. If you solve the new momentum equation, F equals dp dt, it's harder, and this is the solution you get. You get the speed of the particle as a function of time, v of t, that's the inset at the bottom of the white space on the graph. It's equal to the force times ct. Okay, that's linear. That increases like t doubles, it gets twice as big. T triples, it's 3 times as big. But then there's a denominator, square root of f squared t squared plus m squared c squared. And that thing, as the time gets really long and the particle you'd think would be going fast, that denominator makes the particle flatten out and approach the speed of light. And on this graph, the velocity of light is set to 1, just so you can see it clearly. And so you get completely different particle behavior for a constant force than you do in Newtonian physics. We threw a baseball at 45 degrees to make it go far in Physics 121. If you throw a baseball at 6/10 of the speed of light and compare Newton and Einstein, this is on the moon where there's no air friction. The Newtonian baseball is the blue curve. The Einstein baseball does the red curve. And the reason that it goes both higher and further is because at 0.6 c, it has a lot more momentum to start with than just mass times velocity. It's got this gamma factor jacking the momentum up, and so it goes higher and it goes further as well. Okay, well, what happens to Newtonian energy in relativity. I'll remind you, when we did Newton's laws, we found that there was something that was conserved in isolated systems. Another thing that's conserved besides momentum in isolated systems, and it's 1/2 mv squared, the kinetic energy plus the potential energies that show up and all of that other stuff, the work, the potential energy, the kinetic energy. Let's focus just on the kinetic energy part. 1/2 mv squared. You use 1/2 mv squared to solve lots and lots of problems. Well, it's gone. The energy is not 1/2 mv squared. You've heard of this formula, E equals mc squared, Einstein's famous formula. That's not true either. At least that's not the kinetic energy of the particle. It is an energy, and we'll talk about what it is in a minute. The correct formula is this one. The total energy of a particle is equal to gamma, where gamma uses for its velocity the b squared over c squared part. It uses the speed of the particle. The energy is gamma mc squared. That's the real deal. That's what the total energy of a particle is. So energy is kind of funny now in relativity. We have kinetic energy, we have potential energy, work, we have that, it's still okay, but everything is more complicated. The kinetic energy is not 1/2 mu squared anymore. In relativity, and this just came out of Einstein's calculations when he started doing dynamics with his new formulation of the way velocities transform from one frame to another. It led him directly to this formula for the kinetic energy of a particle. It's mc squared over the square root of 1 minus u squared over c squared minus mc squared, or in our modern language, it's gamma minus 1 times mc squared. As the velocity of the particle goes to 0, gamma approaches 1, and you have 1 minus 1, which is 0. And so the kinetic energy, this kinetic energy is 0 when the particle is not moving. But when the particle starts to move, and gamma becomes bigger than 1, then you have some kinetic energy. Well, if something looks like a duck and quacks like a duck, it's probably a duck. And when Einstein derived this formula and he looked at it, and it had mc squared in it all over the place, and that has units of energy, he said, well, mc squared must be some kind of energy. It appears in an energy formula. It looks important. What kind of energy is it? Well, mc squared is the energy that a particle has when it's sitting at rest with no velocity at all. Once it starts moving, its energy is gamma mc squared. The kinetic energy would be the difference between the two, the moving energy minus the rest energy. But he wondered then if this energy, this rest energy, had real physical consequences. For instance, can you do something with that energy? And it turns out that it is in fact real energy. Here's probably the most spectacular example of this real energy. In this explosion produced by a thermonuclear bomb, the mass of the pieces of the bomb after it exploded are substantially less than the mass of the pieces of the bomb before they exploded. And that extra energy that was lost has turned into this giant atmospheric disturbance called, when I was a kid, a mushroom cloud. I guess you still call them mushroom clouds. It looks like a mushroom. There's less mass after one of these goes off than there was before. Now, this turns out actually not to be that surprising. This is also true of dynamite. The mass of dynamite after the dynamite blows up is less than the mass of the dynamite before it blew up. But the dynamite energy yield is so small compared to this mushroom cloud that the mass difference between before and after is so small that nobody could measure it. And so this wasn't discovered experimentally. This came out of Einstein's equations, was predicted, and then when nuclear physicists started shooting subatomic particles at each other, and they found that there were mass differences between these small pieces. That's when they realized that you could make a much bigger bomb than we had ever made before. When we do particle physics, talk about small things like electrons, protons, and neutrons, it's not convenient to use joules, and you have a homework problem on this. It involves something called volts. You won't learn about that till Physics 220. You don't need to know about volts. It's just an energy conversion. An electron volt is 1.6 times 10 to the minus 19 joules. So it's just unit conversion. That's all you got to know. If you express the rest masses of these small particles in terms of electron volts, they're much bigger than the small numbers you would get if you used mc squared with an incredibly small mass. The electron rest mass turns out to be about half a million electron volts. The proton mass is much heavier. It has a rest mass of about 938 million electron volts. And we'll be using these numbers later in the course when we study nuclear physics. But right now, it's just a unit conversion exercise. Don't stress over what a volt is, although I'll tell you, an electron volt is the energy that an electron or a proton would gain if you let it be accelerated by the electric field produced by a voltage difference of 1 volt. And you will learn about this in Physics 220. So, mc squared is real. Resting objects with more mass have more energy than we thought they did in Newtonian physics. It works the other way too. If you take a spring and it has a certain mass, and then if you compress that spring, which means that you do work on it and add energy to the spring, when you get done, the spring is a little heavier than it was before by tiny, tiny amounts that you couldn't possibly measure. But still, we believe that if you compress a spring, increasing its energy, you also increase its mass. Mass and energy are interchangeable now. They're not separate quantities. You might be wondering what happened to our old friend 1/2 mv squared. After all, 1/2 mv squared works perfectly for speeds that we're used to, even rocket ships. 1/2 mv squared works great. What happened to 1/2 mv squared? Well, it's hiding in Einstein's formula. So let's look at the kinetic energy again. The kinetic energy in relativity is gamma mc squared minus mc squared, or gamma minus 1 times mc squared. Now we're going to use the Taylor expansion to express gamma as not a messy square root in the denominator thing, but as a constant value plus a little bit of change because it's got some v over c, and v over c is small. So the first two terms of the Taylor expansion of gamma are that it's 1 plus 1/2 v squared over c squared. For reference, if you want to know what 1 over gamma is, like you would need in a time dilation problem, it's the square root of 1 minus v squared over c squared, and that's approximately 1 minus 1/2 v squared over c squared. So if you use the Taylor expansion for gamma, then gamma minus 1 mc squared becomes 1 plus 1/2 v squared over c squared minus 1. The ones cancel, of course. And if you look at what's left, it looks like the c squareds cancel too. And you're left with kinetic energy at low speed, low compared to the speed of light, is 1/2 mv squared. Einstein must have celebrated when he got to here, because now his theory makes contact with all of Physics 121, Newton and Galileo. His theory is the same as theirs as long as the speeds are slow, but at high speeds, near the speed of light, he's got the right ones and Newton's is wrong. All right, let's do a little bit of quizzing here. E equals mc squared means that, what do you think? First one is, if mass can be made to go away, you'll get some energy. That's true. But the second one says if something has energy stored in it, it's heavier. Well, okay, that one's also true. If a 1 kilogram mass had 1,000,000 joules of energy added to it and stored in the mass, you will hardly notice that its mass has changed. And that's also true. In ordinary physics problems like all of that heat transfer stuff we did earlier in the semester, those things that had heat energy added to them, they got heavier, but it's so far out, so many decimal places out in the calculations that we just ignore it. It doesn't matter. So here's an example of how to use these ideas. Suppose I give you a proton moving at 9/10 of the speed of light. What is its kinetic energy? So there's the mass of a proton. So you do this. You'd first find the rest energy of a proton. So you take 1.673 times 10 to the minus 27 kilograms, 3 times 10 to the 8 meters squared per second squared. That turns out to be joules. That's what the units are. That's 1.5 times 10 to the minus 10 joules. We don't like dragging around 10 to the minus 10 kind of stuff. So we convert it to electron volts, and it's 938 million electron volts, as we had on the previous slide. Now we figure out what the gamma is. So that's 1 divided by the square root of 1 minus 0.9 squared, because the c squared in the velocity squared and the c squared underneath cancel. That's 2.3. If you then calculate gamma minus 1, that's 1.3. And so the kinetic energy is 1.3 times 938 million electron volts. So a proton moving this fast has more kinetic energy than it has rest energy by a little bit, 30%. And that's how it's done. That's how you find these things. So here's another quiz question. When this mousetrap is cocked and ready to snap shut, it has more mass than just before it was cocked. True or false? Let you think about that. The answer is, that's true. It's a little heavier, way out in, I don't even know how many decimal places it's out. It's further out than you could measure, but it is a little heavier. All right, so that's what we're going to do with relativity. I have good news and bad news now. The bad news is that from now to the end of the semester, everything is really hard and really weird, and I'm going to sound like I'm deranged. The good news is that the real problems you can do with this stuff that's coming up are so mathematically difficult. Use mathematics that you haven't had yet. So they're so hard that I'm not going to assign any problems like that. All you have to do is understand the qualitative drift of things and put numbers into formulas from the book or from the chapter summaries. It means the class will now turn into Physical Science 100. So here's the summary. F equals ma is gone, replaced with F equals dp dt, just the way Newton did, except that P is kind of funny. It's not mv anymore, it's gamma mv, where the gamma uses the speed of the particle in the square root of 1 minus v squared over c squared. Momentum is still conserved, energy is still conserved, and Newton's third law is true. So the basic stuff that we did in 121 is all still true, but the formulas for things are a little strange. There is this idea of rest mass. Particles have energy stored in them just by virtue of having mass. If the particle is moving, if the mass is moving, then its total energy is gamma times mc squared, and the kinetic energy is the difference between the moving energy and the rest energy. It's gamma minus 1 mc squared, and if v is really small compared to the speed of light, this turns out to 1/2 mv squared, just like Newton said. We find that nothing can go faster than the speed of light, and that fast objects have extra inertia because of the factor gamma. Okay, and then there are some questions for next time, and I will see you next time on Friday.